Let's try one more. This time we'll see how to calculate the second derivative. So we have the equation x to the fourth plus y to the fourth equal to 16, and we want to calculate y double prime, the second derivative. How do we do this? Well, if we want the second derivative, we need the first derivative. We need to get that first. And as this equation is written, it's not written in the form y equals. So as this equation is written, we have to use implicit differentiation in order to calculate y prime. So let's go through that again. We've done one similar to this before, but just for the practice. So we write down our equation, and then we just go term by term and we apply the derivative. Addition signs and subtraction signs kind of tell us where the terms get split up. So we'll apply the derivative to the x to the fourth, apply the derivative to that y to the fourth, and then on the other side we'll apply the derivative to 16. Now we go through and we just differentiate like we've been doing. So this is an x term all by itself, so differentiate it like usual. So power rule tells us that derivative is 4x cubed. Then we have a y term all by itself right here, this y to the fourth. So we're going to differentiate that like usual. So 4y cubed, so just regular power rule. But because this is a y term, we multiply the result by y prime. So we're going to multiply by y prime there. And then on the right, derivative of a constant is 0. So once we get to this point where we've finished differentiating, there's no more derivatives to calculate, we kind of enter the second phase of our process, and that's to solve for y prime. So what we want to do is we want to get all terms without y prime. So we kind of read along and identify all the terms that do not have a y prime. We want to move those to the other side. So we would subtract 4x cubed from both sides just to move it over. And when we do that, we get 4y cubed times y prime is equal to negative 4x cubed. And then once we have all the y prime terms all by themselves on the left, then we want to get y prime all by itself. So that means we're going to divide by this 4y cubed. Divide both sides by that 4y cubed. And that'll give us y prime all by itself there on the left. And then we have a 4 divided by 4, so maybe the 4's cancel. We have negative x cubed over y cubed. So there's our first derivative. Not too bad. We've done one similar to that. Kind of interesting to graph this curve out. So we've looked at x squared plus y squared equal to 4. So that was the circle of radius 2, the kind of the inner one here. The graph of x to the fourth plus y to the fourth equal to 16 kind of has a similar shape. It's kind of circular, centered around the origin, but it has this boxier look to it. And if we were to kind of increase the exponents, if they were both 6s, it would just become boxier. So kind of fun to graph the curves out. X squared plus y squared gives us our usual circle, but if we have these higher exponents, kind of a circular shape, but it just becomes more squarish. All right, but not necessary for actually answering the question. Y prime is equal to negative x cubed over y cubed. We have our first derivative. Now we need we want to calculate our second derivative. So that's what we're going to do next. We're going to calculate y double prime by doing implicit differentiation again. All right, so we calculated our first derivative. So let's write that out. Y prime is equal to negative x cubed over y cubed. And to get our second derivative, we just differentiate again. So apply the derivative to both sides, going term by term. Now this negative is a constant multiple, so I've just kind of left it outside of the differentiation process. We know we can do that with constant multiples. All right, what do we get when we differentiate the first derivative? We get the second derivative. So we're going to get y double prime. And when we look at this fraction, it's x terms, it's two functions of x essentially being divided that we have a fraction of here. So we have an x cubed on the top, that's a function of x. We have y cubed on the bottom, but y is an implicit function of x. So really there's like some hidden x terms in here. So we have two functions of x that we're dividing. We need to use quotient rule. All right, so how is that going to look? So that constant multiple of a negative, let's just put that in front. And now let's work with the quotient rule. So we start by writing down two copies of our quotient, top times bottom. We write them as a product, top times bottom. And then a second copy, top times bottom. In the first copy, we apply the derivative to the first part. In the second copy, we apply the derivative to the second part. And then we put a subtraction sign in the middle. And then we draw a big fraction, and we square the original denominator. So it was originally y cubed. We're going to square that. And then really, there's this additional negative out front from the fact that we had a constant multiple there. Okay. So now we want to keep differentiating. So we have this x cubed to differentiate. So that's just an x term. We can differentiate it like usual. So when we do that, we get 3x squared. Then we have our y cubed there. It's outside the brackets, so we're done with that. Then we have minus x cubed. And then we have this y cubed term that we need to differentiate. So differentiate like usual. We get 3y squared. And then we multiply that by y prime because we're differentiating a y term. So that's the only thing that's important to keep track of here is whenever we differentiate a y term, we multiply the result by y prime. All right. And then we divide all of this by, we can maybe simplify this. So when we have multiple exponents like this, we have y cubed all squared. We can just multiply those exponents. So we get y raised to the power 6. All right. So when we look at this, we want our derivative in terms of only x and y. So that wasn't a problem for our first derivative. There was only x's and y's here. But in this second derivative, we're done differentiating, but we have this y prime right here. But we actually know what y prime is. It's negative x cubed over y cubed. So we can actually replace that y prime with what we know. It's negative x cubed over y cubed. So we can fill that in. So when we do that, we get y double prime is equal to negative 3x squared y cubed minus. Now when we put this in, it's helpful to kind of, as we're going along, it's helpful to kind of rewrite the term. So I'm going to take this 3, put it in front, and then kind of keep things in alphabetical order. So x cubed y squared. And then for that y prime, instead of y prime, that's where we're going to fill in the fraction there. So negative x cubed over y cubed. And then this is all over y raised to the power 6. And from here, that's pretty good. I mean, we could simplify this down, but that's pretty good. So what could we do to clean it up? Well, we have a double negative, so bring this negative out front, and it'll make that positive. We have a y squared here, and then we're dividing by y cubed, so we could cancel some of the y terms. And then we could consolidate the x terms here. So what might this look like? We'll have a negative in front, 3x squared y cubed. We'll have a plus 3. And then if we combine those two powers of x, we'll end up with an x to the power 6. And then y squared divided by y cubed is just going to be 1 over y. And that's all over y raised to the power 6. If we wanted to go a little bit further, we could maybe we don't want to have fractions on top of fractions here, so maybe we could multiply the top and the bottom by y. This is all completely not necessary. We're just trying to make this look a little nicer. So this is, we could actually stop right here. This is fine. But as usual, it's helpful to, try to simplify, at least some easier simplifying. So if we wanted to, we could multiply this fraction by y over y. And what that would do is we would distribute into this numerator. So we'd multiply a y in here, and then we'd multiply a y in here. And why that's helpful is it's going to get rid of that 1 over y. So it's going to be negative 3x squared y to the 4th plus 3x raised to the 6th all over y to the 7th. Now actually, sometimes you can do a little bit more. We can actually factor out now a 3x squared in this numerator. So if we do that, we're left with a y to the 4th. And then over here, we're left with 4 copies of x. So we're left with an x to the 4th. And this is all over y to the 7. And then y to the 4th plus x to the 4th, we actually know what that is. So this doesn't always work out like this, but it's actually kind of nice here. X to the 4th plus y to the 4th is 16. So this whole thing right here simplifies down quite nicely. This thing is equal to 16 because we're talking about this particular equation. So if we really wanted to, this second derivative simplifies to negative 3 times 16, so negative 48, x squared over y to the 7, y to the power 7 there. So quite a lot of simplifying here. But if you don't necessarily notice all of that, you could stop way back here. But notice how much easier this would be to work with if you go through at least some of the simplifying. All right, so just getting some practice here, calculating derivatives with implicit differentiation. And we have to do this whenever we have just an equation and it's not explicitly written in the form y equals. So we had this equation x to the 4th plus y to the 4th equals 16. It's not in the form y equals, so we had to do implicit differentiation twice to get our second derivative. All right, so that's going to do it for our implicit differentiation section. Now this is going to be a technique that we'll use later on. So we're going to revisit this in the next lesson and actually the lesson after that as well. So good to practice some examples. We'll see you then. Bye-bye.